Hi, this is part 2 of a video lecture about reinforcement learning. So, in particular, we want to uncover the mysteries of trust region policy optimization. And in the first part, we have covered some preliminaries. In fact, we've covered most important stuff, which was natural policy gradient, because it is very similar in the idea to trust region policy optimization. So what we did, let's remember. Basically, we made a small overview of how the most basic policy gradient works, how we define the policy performance metrics, and discuss that we have to actually improve this, in our case, parametrized metric using gradient ascent. And for it, we had to calculate the metric, the gradient of a metric. And so we did that. We discussed some kind of interpretation, what this gradient and how it changes parameter weights, and related problems with it when maybe we change the parameters too much because of some fluctuation in rewards, or just the structure of how rewards are rewarded. And actually, it was the main motivation why we want to introduce the natural policy gradient, is to say that it is so dangerous to basically overshoot in parameter space using gradient ascent. So maybe we have to somehow limit these steps, but not in a geometric sense, but in some kind of approach when we basically move in parameter, like in policy space. And that's why we have introduced the KL divergence. We've discussed KL divergence. In fact, we didn't know how to calculate it, and so we have derived the alternative definition, at least approximation to the second order, using a Fisher information matrix, where we measured the KL divergence between some initial policy or old policy, and this policy perturbed its parameters offset in some distance in this parameter space. So in fact, it turned out that the constituent elements of this Fisher information matrix is just an expectation over gradients of log probabilities of our policy for each basically action which we took in our experiment or trajectory that we sampled. And exactly the same thing was used to construct our gradient. So okay, the kind of what this Fisher information matrix try to tell us is the kind of sensitivity of a policy with respect to some small perturbation. And this particular case, when we compared policy in itself but perturbed, we could call it as a Hessian matrix applied to basically this quadratic approximation. I discussed why curvature is important, because up till now we're using just gradient, which is a first order method, and basically using some kind of metric for curvature we can improve our convergence rate. Basically, we posed the optimization problem where this constraint was enforced, or by our definition, it couldn't be violated. So it's kind of hard, strong constraint, but we've replaced it with just a soft constraint, or we made an unconstrained optimization where we just created a penalty basically using this KL divergence and using this objective function. We have basically defined such parameter changes, displacements in parameter space, which modified our initially used gradient using inverse Fisher information matrix. In this case, it's inverse Hessian matrix also. Then that means that we decided on which direction we should move in parameter space, but we didn't know the step length. And so we, again, using the KL divergence constraint, we've derived the upper basically bound on how large the step size can be. So this is the final update of natural policy gradient, and in fact it's in a sense it is the same update state in a just region policy optimization, except that we will kind of solve this Hessian calculation and inversion procedure using conjugate gradient method. That's a bit overview. So what we will overview of what we did previously, and now we will discuss what we will do here in this lecture. So we will start with the same definition of a performance, but we will redefine how we improve it. It will lead us to some other objective function, which is based on importance sampling. We will basically also construct an optimization problem, maximization, discuss how KL divergence appears there. But then we will actually talk about conjugate gradient, and I will go into detail. I will try to explain to you the idea of or how conjugate gradient evolved, and some other tricks which help us to actually reduce the memory consumption when we actually solve particularly this problem when we use Hessian. But in our basically in interpretation, I mean in implementation that we will discuss, we will basically actually parameterize our policies, and then we will have to calculate KL divergence explicitly, and we will not use the Fisher information matrix. It will be either discrete actions, which is very easy, in fact it's boring, or it will be continuous actions, in fact like n different actions, continuous. It's much more interesting, and we will compare how it's implemented in OpenAI's model. So yeah, maybe what I want to mention is that there's an amazing kind of resource. There's a lecture covering the policy gradient methods. It's very good, in my opinion. It kind of glosses over, of course, all the small details, but pretty much I think it's important to view it, because person talking, explaining, of course, he has much more experience than me, and maybe I will help you to understand small aspects. Excuse me. like the little details of derivations and maybe something that this resource doesn't cover. Just a second. So yeah. So depending on your skill level, maybe if you really understand all the preliminaries, maybe it's wiser to just to take a look at this lecture, maybe return to me, or maybe otherwise I can explain you many steps in detail, and then you can look at this lecture, watch it, and maybe try to basically do some kind of fine-tuning, try to get the important overall ideas that I'm probably missing due to my lack of experience. So yeah, I will link this lecture in video description. And let's start with the trusted region policy optimization. So we are using the same policy performance measure, which is just saying, in fact, they are using this discounted rewards. We will not, but the derivation in a paper uses discounted, so we will just do the same. So it's basically matrix is the same. It's saying we are just trying all the possible trajectories. At least we can estimate it as such. We try many different trajectories, and we are calculating an average of cumulative reward. So we can define something akin to the baseline, which we reward that involves a baseline, which we discussed in a simple or vanilla policy gradient, which is just it's called an advantage function, which is basically your future rewards if you select an action and minus the overall expected reward from this state. So again, it's something that helps to prevent basically giving too much importance to states in which some or all states give larger rewards than usual. But the main difference between our prior definitions is that TRPO is defined basically using this policy improvement kind of metric. It just said that we have some kind of information about the old policy, and we want to ask like how much better the new policy is than old policy, and it can be done via this expression. It's an expectation over trajectories that are taken using new policy, but then the advantages, these rewards, are measured basically using old policy. It kind of doesn't make sense. To be honest, I have completely no intuition why it's so. But the proof is pretty common. It's pretty simple. We just have to remember how we define from classic reinforcement learning, how we define the state action function, which is saying that for regular state value, we're averaging over all actions and taken actions in that state, but Q, the action value is just one particular action and the following rewards. So if we are in state S and take action T, action A, that means that we are transitioning to some S T plus 1 where we receive the reward, and then we add discounted future rewards, which if we follow this policy from this current state, right? And we can just rewrite our advantage in terms of how we define this policy, how we define this action value. So left part is Q, right part is remaining the value function, and then due to linearity of expectation, we can see that we have split the rewards. In fact, the rewards are independent of basically your policy. It's just something that system controls, and then the expectation over many trajectories of all the cumulative rewards is nothing else than our performance metrics for this particular policy P prime, P nu. But then we have two remaining parts. Using some index renaming, we can basically offset T in a sum index lower, but then we start summing to compensate on index higher, and then we can split the right this term into sum of first element, and then starting from 0th element and starting from 1 up to whatever is the length. And actually what we see in this sum is that we are left only with some value state value at some state as 0. And actually we can also think what it means. We have our definition of a value state value. It's just discounted cumulative reward starting from this particular state. Well, in this case, it's just some state and time t, but then we start to iterate with discounting all the future rewards over this trajectory. And actually this S0, we just replace t by 0, and it just pops out that this particular term is just a performance measure for policy pi. And then when we take some expectation over some other policy, is just constant, basically doesn't depend on that policy. So we kind of retrieve that this expression is equals to itself. That means that the right hand side actually works. It's just to prove that this particular definition, like whatever it means, unfortunately, it just works, right? Maybe we can kind of define a function, this performance improvement metrics for our new policy, which will be this difference. And now we have to do something about the fact that we are sampling expectation basically over a new policy, which we haven't done. Our goal is to basically reuse old data for old policy which we know, and the trajectories we know. And if you're familiar with what is important sampling, it's not a difficult concept. In fact, I can just take 2 minutes to derive it because it's so simple. Just say we have some expectation of some function over some probability distribution p. It's just a weighted sum of this particular value. Again, this can be just x, and we will return the average or mean value. And it's just saying that we can multiply we have some kind of other distribution which we call q, and then we can multiply it by a ratio of 1. And basically rewrite the same definition using, let's see, f of x. We will keep what we will keep p divided by q. One q of x is remaining. Well, it's just saying that this is kind of the same expectation of some other function, but over q. Of some other function. Well, what it means is we're sampling. We know the probability distributions over both functions, but we have data over some function, and then we can kind of want to rescale the values of f some. Yes, this whatever f is, mean, deviation, some kind of, I don't know. We want to rescale it, variance, I mean, such that if in some distribution the probability of some particular this random value is low, it basically this ratio will say, I will compensate it, I will be high. You can just follow through. It's very simple and kind of logical, except that you have to the distributions, they have to overlap kind of everywhere where it's important. It's the thing that you could see in classic reinforcement learning. Probably it was Monte Carlo, where it was called offline off-policy learning. And the idea there was that if you want to compare two policies, at least these policies have to visit the same states. And so just the probabilities shouldn't be zero in your trajectories, basically somewhere. So, okay, this is the important sampling idea, is that, okay, maybe we should just resample this expectation over different basically distribution of fault policy. And it's not that simple, unfortunately. In the paper and also in this lecture, which I propose you to watch, they kind of change the point of view of how we express the policy performance in terms of kind of visitation frequency. What was it called? Yeah, visitation frequency, discounted visitation frequency. It's kind of difficult. I personally don't completely understand it. What I can understand is to use, say, let's define a metric in such that we will go over all the states and we will basically average, depending how often we can encounter. There's a probability of encountering this particular state using this policy. We can make a weighted average of all the rewards from all the states, right? And we can basically rewrite this V again as an expectation over all the actions of action functions, action values. So this is kind of form that's it's very akin to what authors use in paper, but in this case they kind of invoke also the temporal aspect. So it's kind of more difficult at time t. There is a probability that our agent will be in state S, which is kind of crazy. But let's just abstract. Let's not think about it. But yeah, they rewrite expectation over this probability visitation frequency over pi. Again, our definition used new policy pi prime, and also we compute expectation over actions of our advantage discounted. We can notice that there's a sum p and gamma, which is in the definition, of this distribution of visitation frequencies, and we can just rewrite this all this expression in terms of this particular distribution, which is is dependent on policy. So different policies will basically explore different parts of space, observation space. And then actually now we can implement the importance sampling. We just say, okay, we introduce this ratio. It will just cancel something, not cancel, but we will rewrite as subdefined here. And then we can basically say that, okay, not say, what we see is it's a expectation over policy, not new, but old. That's cool. But then we can still see that the state frequency visitation is still a sample from this particular distribution, which is related to new policy, and we cannot do actually anything about it, not explicitly. So our best choice is to basically say, okay, let's consider that the policies, that this particular distribution is similar in both cases, between old and new policy. What you could say is, okay, I just replace this particular expectation over something, but yeah, I think it will be proper to just introduce another ratio here, which will be d of p prime over dp, for it's a function of s, both of them of states. And then we actually change the expectation over old distribution, but then we say, okay, in every state, for every state, this basically ratio is 1, and then we kind of cancel it. And this is exactly this point, inflection point, I don't know how to call it, where we make some kind of approximation. We are assuming that this particular value, I just forget, frequency discounted frequency visitation of frequency visitations, whatever, you get it. So in this particular case, we just say, okay, our policy should be comparable, at least similar, very similar, for this approximation to work. And then we will basically undo all the steps that we did prior, using this from these frequencies and actions to basically our old expectation over trajectories, and we get this expression which is central to TRPO. We can return a bit to the question, what does it mean for the state visitation frequencies to be better, not better, but similar? Well, if you think about it, in order to visit same states with same frequency, it means that the policies take similar actions in same states. And actually, this is the point where the KL divergence comes into play, that we will have to compare KL divergence for a particular state, at least all the states that we've gathered over trajectories, and over the actions, just to know that they're similar. So let's define this particular, we have defined previously, okay? So we just rename it. Maybe, yeah, we change the notation that we go from primed policies or not primed to some just policy parameterized by theta old or theta t plus 1, which is t in this case should be iteration. Kind of we measure the experiment with this policy, it's a kth iteration, we just measure the next experiment, it will be k plus 1 and so on. So we define this objective function, which shows you the improvement of new policy over old policy. And then again, we have to calculate its gradient to perform gradient ascent. So this is our objective function. I can show you the gradient, of course. In this case, we just have to take a gradient with respect to new policy, and it will be basically, it won't care about the parametrization of old policy. That means it just goes into this important sampling ratio in the top part. But actually, in our implementation, we won't use it. We just compute the gradient using auto-differentiation. There are some comments about this particular expression, but I'm not sure about, honestly. It's just saying that if we basically expand probably old this performance measure matrix, if we expand into like constant and linear, so Taylor expansion of zeros on the first term, we will see that actually they have the same gradients. I'm not sure how significant it is. And then the question how we will actually, it appears that we don't actually need this gradient again, or maybe we do. Yeah, we will need it, but still we have to pose this optimization objective, similarly what we did in natural policy gradient. Where was it? So exactly this same stuff. It looks kind of different, but still it's about the same. So we just take the linear expansion over this improvement metric, which means we have the constant term here evaluated at theta alt. Well, maybe I should have written that this is theta alt plus some delta, which is some theta nu, basically. But okay, this is this left constant term, this, and the linear term, which is the gradient. It is here, of course. If we take a gradient with respect to alt, it kind of vanishes. And we reuse our KL divergence approximation up to second order. We don't use Fisher information here, we just define it like explicitly in terms, or implicitly in terms. We don't show the contents, basically, it's implicit, where we will have to calculate the Hessian matrix. And our objective function, of course, is to maximize this approximation with penalty, similar as we did previously. And we will find this particular update rule. It's the same as in natural policy gradient, except we replaced Fishers with Hessian, and we will have to find the step, but it's just an outline, basically just to show you that actually that nothing really changes. We return to the question of KL divergence again. We will have to compare the action distributions. So for every state, we have to compare the distribution of actions if they are similar. And the paper said that original theory, because we have unrolled the whole trajectory, we have to compare it for all the choices. and then take the maximum, but the paper said, okay, it's just more stable to compute the average over all the encountered states in our trajectories. Just a small recap again. In NPG we used Fisher information. In this case we just don't go as deep. Our policy update was such, it still remains the same. But now we can actually solve this interesting issue that computing Hessian of KL divergence it takes a lot of computation, and it takes a lot of memory because it's n, and we have n parameters, and we're just, remember, like in Fisher information, we take outer product of gradients. That means that this is n by n matrix, and the second problem is we have to invert it. So it's a double trouble, actually. And this is the point where conjugate gradient method comes in. Of course, you can do the same as we did in natural policy gradient and just invert it. But this is kind of one of the central ideas of how would you actually implement policy where we have a lot of parameters. And here we will make a huge a tangent into conjugate gradient. So there's a interesting resource that covers the kind of, not the history, but the general how to derive the conjugate gradient. So you see it's like 60 pages long, but it covers basically starting from what? So starting from which idea we derive. So we start with steepest descent, and we go derive conjugate directions and then conjugate gradients. So I want to talk a bit about it. So if our initial goal is to solve basically problem ax equals b, that means we have to find some kind of solution x star, which is a minus 1 times b. And actually that's exactly what we want to do in our case. In our case, it's just h minus 1 b. So our conjugate gradient will actually give us a solution. This. And what this method tells you, if you have this particular problem, ax times b, we want to invert a, but instead of us trying to invert, we create this quadratic form. There's some considerations that this a should be positive semi-definite, which means if it was two-dimensional, if it was one-dimensional, it will be just a parabola pointing up. That means that it has this unique minima in two cases. In two dimensions, it would be paraboloid, what it's called. Yeah. So that's the idea, which should transform this ax equals b into some kind of quadratic function, and then we turn it into optimization problem, which means if you will see that assume that we take a gradient of this particular objective function, skipping all the maths, we will see that what we get, given that a is also symmetric, which in case of Hessian, of course, it is. And maybe I will show you why it's positive semi-definite, right? Okay, so if we take the gradient, we see we get expression that it is ax minus b. So if in some special point x1, which is the minimizer, we will get gradient of x at this point is equal to 0, and in fact in this particular point x star, it solves our initial problem. So that's the idea. We transform this matrix equation into quadratic form, and it's optimization. And one of the what's cool about this method is that we have just defined how to compute a gradient using nothing else, just to matrix multiplication and by vector and subtraction. So it means that at every x we have access to our gradient. And guess what? Using gradient, we can use gradient descent basically and to find this minima, this x star. There are some definitions. Kind of the author changes the point of view from in terms of error, how to solve it, some kind of isolines of this objective function, and we move somehow. It's not movement along a gradient, and it defines a point of view from errors. So basically we want to reduce this error vector, and when this error vector is 0, we are at center. It's not kind of important, but still, that's why it's kind of difficult to follow sometimes. And so idea is that we pick some kind of, yes, we know where to move in the gradient descent. One interesting fact I want to tell you. Let's say we don't know how the objective function works. We only know that the gradient basically points in a line that's orthogonal to tangent of an ice surface. It's such a direction that basically is the shortest distance between two ice surfaces. So here it's 1, basically value some kind of here is 0, next is -1. It just selects the shortest path between them. And this tangent. But what's okay? Let's consider that we have objective function that is just a parabola. So in fact, our gradient will point straight into solution, but it's not always the case. Yes, in fact, we have some kind of a tangent and basically normal, but we don't actually know the shape of actual objective function. It can be like this. Well, it's not precise, but you get the idea. Or it can be something like this. Tangent is the same, but say here the minima is here the minima is here. So in fact, gradient descent, it only reduces, we have only guaranteed that it reduces the objective function in this direction, but it doesn't point there. We have to obviously make many steps, or not many. Also, we have to know actually how far in this direction we should go. And that's the next question. How to find how far? We know the direction. And it boils down that we just parameterize this exploration direction by basically extending from some x0 some kind of vector d naught, we just scale it and search along this direction. So we parameterize this search direction by some kind of step, basically exploration step, and then we plug it into our problem, and then we can actually find it is kind of it becomes a one-dimensional function. We take the derivative to find the minima, and then we actually can express this step length using our displacements. Here R is kind of gradient or against the gradient properly. Like I said, there are a few redefinitions. So we can actually define gradient descent. We know the direction and we know how far we should go, which probably closely mirrors what we did previously, but again, it is optimization. And what we observe, and you can prove it easily, that gradient descent moves in such a way that then each next exploration direction, which is again against the gradient, will be orthogonal to previous direction. And it's kind of problematic because if we know that true solution lies somewhere on this line and we are moving in these zigzags, basically what you can think about, yes, it does kind of comes closer, it comes closer and closer, right? But still, if you just can view it, this problem is that our initial exploration, it introduces some error that the next exploration tries to fix. It kind of fixes, but still it overshoots just math works like that. And the next tries to correct previous error, but still does some exploration and such, and it just continues, and it converges, but amount of iterations that it took, it's large. If you compare it to second order methods, Newton's methods, you just start somewhere, it reads the curvature of space of this objective function, it just shoots in one iteration straight to minima. But again, there's a trade-off. It's a second order. It means that you have to calculate something other than gradients. And the main idea, the meat of the conjugate gradient, it is idea of conjugate directions. It actually tries to basically change, improve this, or negate, I don't know how to fight this idea that each other iteration, it produces some kind of error which has to be corrected by the next. And I don't know how to motivate the idea behind conjugate directions properly. But there's the idea that we can measure the angles differently by knowing the parameters of this paraboloid. Basically, this matrix A, it contains our quadratic terms. And using this particular metric, it's kind of, I don't know, A can be viewed as some kind of metric tensor, something that's responsible for the curvature. Basically, if we move in Cartesian plane D, then A corrects for some deformation of this flat plane, something like this, something like in relativity. I don't know. It basically something very similar. And so idea is that maybe I forgot to tell you that the conjugate gradient, it solves the inversion of n by n matrix in only n steps. And so it means it kind of explores only n times. It does line search only n times, which is interesting. And so idea is that we define n directions, which are not, of course, which are linearly independent. And then we use this metric to basically orthogonalize it, but not in a typical sense, but in a conjugate orthogonalized sense. It means it uses this not curvature, but basically curvature idea. And maybe you remember that there's such a procedure as Gram-Schmidt orthogonalization, where the idea is nothing else that we just get a set of vectors that span some space, and then we take one of these vectors first as some kind of reference or starting point, and then every next vector we just subtract. We can decompose that next vector into basically parallel and perpendicular parts of our original vector, and we just subtract everything that is perpendicular. We subtract all the parallels, and it's just by this construction it leaves only perpendicular parts. And for third vector we just subtract perpendicular parts from first and the second, and so on and so forth. So that was the idea for conjugate, for Gram-Schmidt process orthogonalization, but we can kind of implement this measurement of dot products or distances or angles if we replace this a inside, and it just straight up turns into new kind of conjugate Gram-Schmidt orthogonalization. And in fact, this gradient, this conjugate direction method, again, you supply just a list of n vectors, you orthogonalize them, and it turns out, like in this example, u1 and u2 are something that are not that are independent, basically, and which we orthogonalize into d1 and d2. Of course, we just simply pick first vector u1 as d1, and then we orthogonalize u2, and that's how it looks like. It was basically red and black turned orthogonalized, conjugate orthogonalized into blue. And we see that miraculously this algorithm just solves the problem in only 2 steps for a 2-dimensional problem. For many directions, it's not directions, dimensions, it's kind of more difficult, but there's one important aspect that I would like to discuss. So in 2 dimensions, we see only the iso surfaces. In 3 dimension, we will see some kind of, so 2-dimensional, this iso surfaces is a slice of some kind of 3-dimensional objects for 3-dimensional problem. But basically it is some kind of paraboloid. I am drawing an iso surface of a paraboloid. So this is the external boundary, the front and the back. So idea is there's such a notion as Krylov space. I don't know. I want to tell you why it solves basically in n iterations only. It's at least some kind of hint at this, and it's related to Krylov space and how this method covers 1 dimension at a time, basically. You can imagine that at least we start at some point, we give this list of directions, and we start with some initial guess. Let's write here. We search along this direction and you can imagine it's a needle that pierces some kind of onion, where each layer of the onion, of course, is in like an isosurface, and closer to the center, the smaller the value of this onion layer is. And so it kind of pierces through, it searches, it can minimize it, do whatever interpretation you want for minimization, but it knows where it reached the smallest value. And then we supply the second direction. And the question is, we have to orthogonalize it, basically. Now I think about it, we actually supply, it kind of changes how I thought about it, but just suppose that there is a kind of plane to this line in which all vectors are conjugate orthogonal, right? Just suppose that we take this particular sum of them. If we look at this paraboloid from the side, this kind of needle or line search points at us. All the orthogonal vectors are in this plane. So we just pick something. It can be, I don't know, kind of whatever arbitrary directions. And it starts line search in this direction. Of course, kind of our minima is somewhere here, so it will start searching in this direction, and it will at some point, I mean, it will know actually where it is already. It will minimize it to some solution. So in fact, it moves somewhere in this direction. It's maybe hard to understand, but this is kind of, I'm drawing actually orthogonal, but it should be conjugate orthogonal, and it basically reach inside somewhere as this layer of onion, which is minimal at this line, right? And then we get this same orthogonalization problem. There's some kind of choice of orthogonal, of which vectors are orthogonal, right? And in fact, in our case, what we have to, the limitations are such that it should be orthogonal to all of the previous vectors. So kind of this previous orthogonality imposes some restrictions on whatever is picked now, and it has no choice is to move, in this case, to the center. But you can think about it, the fact that our second iteration moved somewhere orthogonally, it kind of means that we have basically, after reaching this minima, we have kind of explored the plane. So at first we have explored the line, then we moved orthogonally somewhere else and find a minima there. And because it was from one minima to another minima, we kind of explored the whole plane in a sense. And then when we add additional dimension of exploration, we kind of extended the exploration space, this plane, whatever it is. We kind of expanded it. We search multiple planes, or we extended this plane, I don't know. But basically, we extended the search dimensions into this cube, rectangle, whatever it is, parallelepiped. And this is kind of the idea behind why it can solve the n-dimensional problems in n steps. It starts from a line, plane, cube, whatever else, four-dimensional stuff, whatever else, until it reaches. In fact, it's so efficient that what they write in a paper, I don't remember how many parameters they had, but yeah, they used like 10 iterations for to approximate it very well. So it's kind of crazy. So it's the main benefit that we don't even have to. First of all, our measurements of Hessian may be kind of noisy, but then we can kind of make it even faster by reducing the number of iterations. That's why the algorithm says use just n iterations. So that's the idea behind conjugate gradient. The actual implementation, of course, it is basically what it involves. Now kind of the second part of the question. Due to the fact that we are using Hessian, there is one simplification that can be made. So the original conjugate gradient, it works like, maybe I have it. So the algorithm is such that we give some kind of initial guess, but then what you can see that our A matrix, which is Hessian in our case, is multiplied by one vector once, and then this A multiplication with another vector you used here two times. Yeah, 2 times. So the idea is maybe we can kind of find some kind of trick that will help us to do even more calculation, and there is such a trick. That's why I wanted to show you that there are a particular step where this A, our Hessian, is multiplied by some kind of vector. And the idea is such that we can decompose the Hessian. We have seen it in the last video. We have that we can decompose it, in a sense, decompose it in a Jacobian of a gradient. Maybe you can view it as an outer product of two gradients. And then we observed such expression. If we actually want to calculate h times some vectors v, all right, using this decomposition, which is not a decomposition, but still we can write it as a Jacobian of this stuff times v, but then v is kind of constant with respect to differentiation, and we can bring it inside of Jacobian. And what we get inside Jacobian is just the dot product between two vectors, which is a scalar. And then we take the Jacobian of a scalar, which is kind of transposed gradient. And that's the idea, that we can actually avoid computing our conjugate gradient. It only uses h in this application when it multiplies some vector. And that means that we can actually avoid constructing Hessian, or we only need the gradient of whatever is inside. In our case, it's scale divergence. Then we multiply it by some vector, which will be like an argument. We can construct a function which will calculate this product, Hessian vector product, by pre-computing the gradient of scale divergence, multiplying it by this argument vector, and then calculating the gradient. So this is kind of the idea. Maybe I had examples somewhere. I've described everything that I've told you now, but maybe the implementation, basically inside our conjugate gradient basically iteration, we just again pre-compute the gradient. We define a function that will multiply this AV by some other vector, right? And that's what we see, gradient. Okay, multiplied by a vector and the gradient outside. And then there's an option to actually keep. So it calculates the gradient using the computational graph, and then we have an option to keep it in memory. So in case it computes repeatedly these gradients, it knows where where everything is multiplied together. So it knows that some elements of this argument are multiplied by elements by this and such, right? So it can auto-differentiate when we need it. And so that's the idea. We kind of implement conjugate gradient, just default algorithm, but instead of, say, classic conjugate gradient, when we just calculate inside the loop multiplications a by vector, we define a function, a by vector function. And algorithm actually, where was the algorithm? You see in the TRPO algorithm, we have the update rule. Ignore the AJ for now, but basically it's something that we've seen previously, except there was an inverse here, H inverse. But then if you see that this is the solution of our conjugate gradient, in which we avoided computing Hessian inversion, basically, if you plug it in, you will see the same expression. So don't worry. Here I basically write it out, right? So this is the default. We can replace by H by X stars, but then we have a gradient transpose by H star, but we kind of know what it is, and then we can rewrite it as this. Problem in this definition, of course, is that it involves Hessian, which we don't know. Actually, no, we know, but we didn't calculate it. So kind of this expression is what we actually are doing. And this is just for, I don't know, flex, I guess. And reminder, yeah, we can actually calculate H times vector very efficiently. And now comes the point where when we have to face the fact that we have to actually calculate the KL divergence. In a neutral policy, not a natural policy gradient, we have used Fisher matrix, and we didn't need to calculate it explicitly. We just calculate the gradients of logs and the outer product and such. Also, we kind of did the discrete actions case, and in this case I want to cover the continuous actions. And so in fact we have to understand how to calculate the KL divergence for both continuous and discrete actions. Depends on your application, but I think, again, discrete actions are so boring. I don't even think I have to go through it, but basically, yeah, just, I don't know what to tell you. Maybe the main idea is that, of course, depending on your, either whether your policy will be continuous actions or discrete, it will govern how kind of neural networks are you making, basically the architecture. Of course, it will be, in the simplest case, multi-layer perceptron, but then the question is, what would be the input and the output? And the input, of course, will be just state, because we want to probabilities of some actions in some kind of state, given some kind of state. So the idea maybe could be like, I give you state, give me distribution over probabilities, or I give you state and action, you give me probability, something like that. And it's problematic because probabilities have some these limitations rules, that sum of probabilities should be 1, and the probabilities should be between, including 1 and 0. And it's not something that you can bake easily into neural network. You probably can. But the general approach is to use logits It means that we kind of say you can generate whatever numbers you want from minus infinity to infinity, I don't know. But then over all the actions, I will normalize in such way that it will produce the same properties that the probability distributions have. So of course, the most popular idea is to use the softmax. It has its own problems. It likes to blow up some probabilities and reduce other. It's not linear, but still. And that's the idea. That means that we have some kind of dimensionality of input into neural network, and then we have dimensionality of how many actions in static, in discrete case there are, and it outputs the logits, some kind of numbers that are mapped through softmax into probabilities. In fact, you have to know all the probabilities, right? You have to ask for all the actions because you have to normalize it. There's a practical implementation. You can see it in actual TRPO, this model of OpenAI, but it's kind of boring. It's just basically what they propose is to calculate it using log probabilities. We just have to switch maths around. It's more convenient for. It's not convenient. It's just maybe it's numerically stable because how it treats the very small probabilities. But it's kind of boilerplate. It's so boring that I don't even want to go through it. But the idea is that we just keep the log probabilities for all the states and actions. Basically, we observe all the states, and then we extract for all the observed states all the probabilities of action, and when we just take the log probabilities and then we deal only with, and then we change our math a bit using exponentiation or the properties of logs to get our result. And well, like in this example, you want to extract this fraction importance sampling ratio. You have vectorized all your probabilities and then subtract them, take a log, and that's what you get. That will be the main mathematical direction. I don't know how to call it. And then when we reach KL divergence for I forget it. I always forget it. For discrete actions, right? When we reach KL divergence, well, there's just expression for discrete actions, discrete probabilities. It's also called probably not conditional. What was it called? Categorical. So we just replace the integral by a sum. And basically the idea is that we calculate, we compare old policy actions with new policy actions, and then we sum over actions, and then as paper alludes, we take a mean instead of searching for maximal KL divergence. So it's kind of easy and boring. And now the question of continuous actions. First of all, maybe what if we have, it's kind of I have some kind of question head at least. Let's say we have, what if our agent can make two discrete actions, but we have only proved it for one set of discrete actions. And then we have some kind of B1 actions, B2. Well, maybe kind of silly to think about, but still, it still reduces to the case of where we have one single action if we clump basically if we make tuples of actions, so we said we have actions A1, B1, then another kind of single action but composite action is A1, B2, and so on. And then it will have, like, if we have k actions here, n actions here, it will be, for A1 it will be n, for A2 it will be n, so basically it's k times n actions. Yeah, so it kind of, because in continuous action, you can basically calculate arbitrary number of actions, of continuous actions. And okay, let's talk about it. So the most common technique to basically create policies that produce continuous actions is to parameterize them as one of the typical distributions, typically parameterized. Why would we want to do it? Because in most cases, like in this case of normal distributions, all the measures like scale, divergence, and such, it can be pre-computed analytically. That means during each iteration, our program will not have to compute it because we have already done it on the paper, basically. And yeah, so in our case, and this is the case of this OpenAI's implementation and also different implementation in the papers. A paper also mentioned it. Basically, we will use a multivariate normal distribution that has a diagonal disvariance matrix. And so basically that means that all the actions are independent. And also it simplifies our problems a lot. And we don't even, I don't think it's reasonable to think that actions are some kind of related, at least in some approximation, but in general, I think. So what our network should do, basically, it still has an input of a dimensionality of state, but in case of where we have n actions, for each action, it has to output a normal distribution. A normal distribution is it's parameterized by two parameters, mean value and variance, or standard deviation squared. And that means that our network, in fact, it parameterizes state into parameters of a normal distribution. So it inputs basically state, outputs two parameters, from which actually action values are sampled. But in practice, I will say, I'll try that the standard deviations are, it's kind of measure of uncertainty, right? In ideal case, if your neural network can predict, if you view it from a viewpoint of uncertainty and you want to kind of minimize uncertainty, then I would say the distribution should approach basically one true optimal action at each state. That means that it would be some kind of delta function. That means the standard deviation should be reduced. That's the one point. Because in a sense, a large standard deviation allows you to implement exploration. And then I view it as we give it initially all the actions large standard deviation, and we let it explore. And the more refined network is, it should shrink basically standard deviation to make policy optimal. So in this kind of scope, we can produce not two parameters for each state, but produce only mean. It is what statistically policy thinks is the correct version. But then standard deviations are calculated for each separate action, and basically it will be kind of collapsed afterwards. So this is kind of idea. It produces only mean value parameters for all the actions, and sigmas are kept as a separate parameter, which should be constrained. Now we come to the problem: how can we actually sample? Because in case of discrete actions, sampling was easy. We just make a categorical distribution, and it would just, based on whatever it does, whatever it rolls, some kind of maybe normal, not normal, but uniform distribution, and somehow however it works, right? What do we do in continuous case? Well, in this case, we can use this trick, which you can encounter in variational autoencoders it's called reparametrization trick, and there are a lot of tricks and in machine learning, which is kind of hilarious if someone calls something a trick. Of course, in variational autoencoders, they have used this kind of reparametrization because they needed to backpropagate through sampling. We don't actually need it, but still we use it. And this reparametrization is nothing else that kind of a scaling and translation of domain. So scale by sigma, translate the mean into some new location of our mean. And using our basically this normal distribution parameterization, we can actually express probabilities in terms of logs of probabilities. So this is the expression, nothing else. We just take a log of this Gaussian, nothing more. And maybe again we can retrieve it using these log rules, given that we store it in logs, and usually we do. I think this is correct. KL divergence. So KL divergence, right? The fact that we know that the distribution is such, it's normal. We actually can pre-compute it analytically. And there's a whole process how to do it. Maybe just a hint. Remember that KL divergence is an expectation. It's an integral over something. And we just plug in the Gaussians. We take an expectation over whatever is inside, but then we take expectation over some policy, some p, and some values are constant with respect to this policy, and then this is the expectation part. Generally, what we can do, we see that this expectation, for example, over x over policy, so it's px x dx, is just a mean value. We just simplify stuff here, and it turns out that we don't need expectation anymore, given that, well, yeah, we have access to parametrization of our policy. So we get basically analytic expression. And that's what this expression is. And just because how we store it in a model, the probabilities over all the actions or encountered state is just a specific logic there where you basically use broadcasting to calculate this particular function, and then you sum up in a dimension of actions, and then you take a mean in dimensions of states. You know, it's very simple. And is it all? I don't know. Let's think. We have the KL divergence. Why did we need KL divergence? We needed KL divergence because we wanted to calculate conjugate gradient. We needed it because we wanted to calculate H product with V, some kind of action V that we needed for Hessian, and this Hessian was needed for conjugate gradient to determine the update rule. And magically, it looks like we have basically derived the proper update rule. That's it. It kind of ends abruptly, I guess. We can maybe view the implementation. So as I've said, we store many things in logs, and we extract ratios as discussed here, and then each ratio is multiplied like element-wise with our advantages and such. Value function is our baseline. We've talked about it in a part of vanilla policies. So let's see. Yes, in fact, we don't calculate gradient explicitly like I've shown you, and I said that we just formulate an objective function. We calculate the gradient of this objective function. Now there are caveats, because when we are calculating the gradient, it's a derivative with respect to a matrix, and each layer in a neural network is just some kind of it will, if it's linear, it will have a vector of weights and matrix of weights and vector of biases, and basically when you differentiate, you don't get flat. You basically, all the weights are stored as a list of different matrices and vectors. So you have to take a gradient with respect to each of them separately, and then you have to flatten them up, and then you have to manually change neural network weights. Yeah. So kind of you operate in this kind of viewpoint where the gradient, where we have available all the neural network parameters as one vector, right? Not some kind of collection list of matrices and vectors. Yeah, they ask for KL divergence. They multiply or define, I don't know, this Hessian-vector process product. Dumping, I'm not sure about. Maybe regarding the policies, they check, say, if your action space is a box, it means it's a continuous space. It means you just have high and lows, upper and lower bound of domain. In case it's discrete, it calls for categorical policy, and it calls, if it's continuous, for Gaussian policy. So in case of categorical, we just have the logits, as I said, that are their action dimension number of logits. They softmax it. Here they sample it. It's TensorFlow. I don't use TensorFlow, but it's kind of categorical distribution. Here they have kind of I think they have all the actions, and no, all the actions are here stored because they ask for all the actions in logits. In this case, they extract from all the logits all the probabilities, only those that encountered in our trajectories. They do it by basically masking, by extracting only one element. and then summing all the zeros to reduce dimensions. They do it for if we return to the policy, you see actions and states are the same. It's just we have probabilities over our new policy and old policy. And that's the difference here, is that one of them is old. It extracts probabilities for observed action and probabilities for actions that we extract using our new policy. They calculate the KL divergence. In case of categorical, it's simple, right? Again, it's not integral, it's a sum. A probability minus log of probabilities and such. They sum up and take a mean, whatever it means. You just have to follow. I've skipped it because it's just a boring management of dimensions. In case of Gaussian distribution, so we have many actions. In fact, X is a list of observed states. This, for each particular state, there will be a list of action values. So we have two actions which agent takes at each state. It will be just a matrix, in fact, dimensions like number observed states times number of actions. And for every state, it produces some kind of what it expects the parameter of distribution. This log standard deviation, again, it's there are number of actions of this as a trainable parameter, and then we do this sampling, multimodal Gaussian normal distribution, so offset and scaled. Now they call it likelihoods. Questionable. I don't know the proper definitions, because I think it's not a likelihood in that sense. It's just a probability. So likelihood is like a probability, this particular stuff given parameters of our model. Where is it? And then we observe how they calculate the Gaussian likelihood. Let's see. So we see there's minus 1/2, something minus something squared. Well, squared, it doesn't matter the sign here, because I think they have changed the sign here. 2 log sigma, it's just the same. Well, the question is that they reduce the sum up over actions. So it's dimensions of state times actions, and they reduce the second dimension. They collapse it into states, which they later can basically take a dot product of these ratios and the advantages. And, well, maybe you can mention also the KL divergence. So again, you see the inputs are just the parameters of old and new normal distributions. So where is it? Variances. Let's see if it's the same as we calculate. Sum, they do sum in the end, but in our case it's 1/2 sum of square of square of difference, variance, different variance below, -1. It's just the same, right? You can also check the derivation there. So it's, I guess, this is the main stuff. Maybe the conjugate gradient, how they do it. They define the algorithm. It inputs this function. You see this. They say, okay, multiply our Hessian by some vector p. And they do it multiple times, of course. It's just kind of difficult to keep track exactly in this PyTorch definition, but I guess it just covers the main ideas. I'm kind of tired, actually, but let's recap it. We've started from a typical our definition of policy performance, and then we, using our new definition of advantage function, we've defined this policy. I call it policy improvement, kind of metric, but it works, of course. But problem is that we had to change the from which distribution is everything sampled, because we have access to only to old policy data, although we have our new policy. Of course, we have its probabilities. So we did that. We introduced the sampling ratio, and then we actually assume this exactly, that the visitation frequency should be as close as possible, such that we can approximate it at the new kind of visitation, this ratio, as 1. And exactly at this point, the KL divergence comes in and says that it should be basically minimal for all the states for distributions over actions. And then we kind of define second time the improvement metric. I realized that we have to calculate its gradient. We don't really have to calculate its gradient, but we can. To show here, maybe you will see it somewhere else. We define the policy update, linearize this metric improvement, and we keep the KL divergence approximation up to second order. And we have to solve this problem. We retrieve the same step direction as a natural policy gradient. Then again, I mentioned that KL divergence, that we, instead of max, we have to average. So Hessian will be, instead of Fisher, kind of one step back. Our old policy and NPG policy update, we've discussed that using, let's jump here, that using properties of Hessian, specifically that we can write it as Jacobian of gradient, we can simplify the conjugate gradient method, which produces the result of this H inverse G using very few iteration. And in fact, it's not building and inverting H, so it's very convenient. And then this actual update rule, which I don't want to search for it. But yeah, it's defined somewhere there. This will be defined. This is shown in algorithm. It's not particularly correct because we don't know H, how we deal with parametrization, because we have to compute KL divergence actually instead of Fisher matrix. We parametrize in discrete actions. We just, use logits, and then we softmax it. For KL divergence, we actually have to compare all the actions from each state, all the probabilities of actions. We have to compare distributions. That means we can't compare one value to one value. So in this discrete case, and both in the Gaussian, we have to compute probabilities over actions. And then as a subset of this data, we extract the ratios, important sampled ratios, and then the actual full data we use for KL divergence. That's the idea. Continuous actions parameterized use normal distribution, multivariate, diagonal, and our network generates mean vector, and it trains the standard deviations for different actions. That's how we sample. That's how we actually compute using logs our data, and how we implement KL divergence. Again, we sum up our actions. We take a mean over sum up our actions and mean over states. And I didn't talk about line search. So in fact, what we've covered up until now, it's called truncated natural policy gradient. Because we do approximation for Hessian quadratic approximation, we cannot be sure that the actual result would be precise. It means that we don't know that KL divergence will hold under our approximation quadratic. And up until now, we assume that that's correct. And in fact, our step length may be too large for it to hold. And TRPO is actually, after we computed the conjugate gradient, we say, okay, we will kind of try our current estimate for step size, and then we start kind of reducing it until the KL divergence is not violated anymore, and the policy actually improves. So it's kind of, you can read it here in code. They say if your algorithm is natural policy gradient, in fact, it should be truncated because they use conjugate gradient. Otherwise, it performs backtracking. And so you see they have some kind of iterations for backtracking, this J. And then they take a power of this. They evaluate KL divergence. Again, it's hard to check here because of how they use placeholders and such, at least to my understanding. But yeah, they reevaluate it using again recalculating this all conjugate gradient stuff. I'm not sure if they have to calculate the whole way, but yeah, still. So it's kind of the last step until we reach TRPO. Maybe it's kind of anticlimactic, but actually that's what this algorithm does. Again, I think it's useful that you watch this video and maybe try to catch this small, some kind of facts that I couldn't convey you. in fact, there's a lot of interesting still information for me there. So I wish you success in your research, and maybe see you in next video.